Hello everyone, this is BUSML 7247 Analytics for Macro Marketing Data. This video is Lecture 12, Machine Learning, Big Data, and Artificial Intelligence. In this lecture, there are two required reading materials. First, Detecting Influenza Epidemics Using Search Engine Query Data by Jeremy Ginsberg and his colleagues, published at Nature in 2009. Second, The Parable of Google Flu, Traps in Big Data Analysis by David Lager and his colleagues, published at Science in 2014. Both articles are available in Kerman. In this lecture, I first introduce basic concepts of machine learning. Machine learning is a very broad concept of statistical techniques, so understanding what it is, how it works, and when we use it requires mathematical foundations. But don't worry, I'm going to deliver the basic concepts, minimizing mathematical expressions. Those concepts will be delivered with marketing examples. Then, as we discussed with Weddell and Cannon's Data-Rich Environments article, machine learning is a suitable solution to handle big data. The term big data does not stand for just a large size of data. Beyond the size, big data have favorable properties that provide new opportunities we've never experienced. Google Flu Trends is one of the famous attempts of using big data, but it was finally failed, giving us an important lesson of how to use the big data. I briefly introduced what was going on for your better understanding about big data. Next, another important concept is AI. It is a broader concept than machine learning and was suggested a long time ago. Recent advances in computational methods, which is called deep learning, AI is now widely used in real life. I will briefly introduce what we can do with deep learning algorithm, especially for marketing. Alright, are you ready? Then, let's get started. Conceptually, machine learning includes all we've learned in this course. Any systematic, replicable process to understand data and extract value of information from data is a machine learning method. Machine learning can be defined as a study of methods or algorithms designed to learn the underlying patterns in the data and make predictions based on these patterns. The key point is that the purpose of machine learning is prediction, and it is what differentiates machine learning from traditional statistical methods. Traditionally, econometric methods have been widely used for data analysis. An example is OLS estimator for linear regression. Those methods focus on causal inference about an effect. For example, managers are interested in knowing if increasing advertising expenditure really causes an increase in demand. Econometric methods and applications have been studied to find unbiased empirical evidence for the proof of the causality. Machine learning methods are philosophically a little bit different, focusing on the predictions. For example, consider a decision-making problem of banner ad choice. It is not necessary to show that the banner ad really drives clicks and sales to select one of ad options. Instead, managers want to know which one will generate more clicks and sales. Most broadly, there are two types of machine learning methods. One is supervised learning. Supervised learning is close to precisely the same as what we've learned. They are predictor or independent variables and a target or dependent variable. The goal of supervised learning is to predict the value of the target variable given the predictors. Conceptually, supervised learning is very similar to a class in a school. Researchers give the machine some data as examples, which is called a training sample. That's why this is called supervised learning. The machine learns from the examples and then takes a test with other data, which is called test sample. From the test, the machine is evaluated in prediction performance. Examples of supervised learning is decision trees, neural networks, and regression analysis. we will revisit regression from supervised learning perspective. The other is unsupervised learning. Unsupervised learning does not distinguish between variables in data. The goal is to look for patterns, groupings, or other ways to characterize the data. In marketing, we've already used various unsupervised learning methods, including cluster analysis, vector or principal component analysis, EM algorithms, and topic modeling for text analysis. Alright, now let's dive into supervised learning with the linear regression. Suppose that we are looking at weekly sales data, and with consideration of price effect and in-store promotion effect, as in this regression equation. This equation is a simple log-log demand model. Log sales is modeled as a linear function of log price and in-store promotion dummy. Machine first learns from training sample. In this regression, we want to know alpha, beta, and gamma. Let's say A, B, and C are our best guess on those coefficients. One solution we have is OLS estimator. This is an unbiased estimator, implying that if the model is true, expectation of OLS estimators of A, B, and C are the true value of alpha, beta, and gamma. This is a desirable property of econometric methods. But supervised machine learning's approach is different from the OLS estimator. Supervised machine learning draws predictions given A, B, and C values for test sample and find the best values of A, B, and C to minimize prediction error. The prediction errors can be decomposed three components. First, inherent errors in data, epsilon. This error is irrelevant to the predictors and the target variable, so prediction errors coming from epsilon is irreducible beyond our control. Second, bias. This is a systematically expected or average deviation of our guess on the coefficient from the truth. That is, it is coming from difference between A and alpha, B and beta, and C and gamma. Third, variance. This is also coming from our guess, but different from the bias. It is about uncertainty of our guess. Now I'm going to give a stylized example for your better understanding on the bias and variance. Suppose that the regression is truth, and an in-store promotion increases sales, but just small, like 10 units per week. And there are 100 observations with the in-store promotions in the training sample. Mostly just marginal increases in sales observed, but suppose that there was one observation with a huge, like 1,000 units, irregular sales increase with the promotion. And suppose that we have two machines. They don't know what truth is, so they don't know that the irregular observation is a false signal. The first machine, Anna, says, "It's an outlier, just a weird observation, mostly marginal, so let's simplify it. No in-store promotion effect." That is Anna's guess on gamma. The C value is 0. The second machine, Elsa, has a different opinion. She stops Anna and says, "Anna, wait, what if it's true? We have to keep some units for the in-store promotions just in case. How about 100, 200, or 500? That is, Elsa's guess on gamma, the C value, is quite big and uncertain. And now let's evaluate those ladies' predictions. First, Anna's prediction scheme. It is a simplified or restricted scheme. The truth is that the in-store promotion effect is small but present. So her prediction will be, on average, smaller than actual sales. This deviation is systematically expected because of her biased lens, which is simply ignoring the promotion effect. Second, Elsa's prediction scheme. Her scheme is more detailed and complex. The truth is that the in-store promotion effect is present but small. So her prediction will be, on average, too much. This error was due to sticking on all possibilities that she observed. Elsa predicted in doubt, that is, her prediction has high variance. The difference between Anna and Elsa is called bias-variance trade-off. Anna has simplified the model, that is, complexity of the model is low. So her prediction is biased, but it's drawn for sure. That is, most prediction error is coming from the bias. While Elsa has made the model complicated, her model is relatively complex. Her model does not have bias. She found, anyway, the effect correctly. But the problem she faced is her prediction is uncertain. Sometimes, the error coming from high variance is greater than the error caused by high bias. What about Anna and Elsa's prediction schemes? First, in training sample, Elsa considered much more of information in data than Anna. Elsa tried to explain all possibilities observed in the data, but for the test sample, as a true in-store promotion effect is small, Anna's prediction error is highly likely to be smaller than Elsa's prediction. Then, although Anna's prediction always incurs a cost of bias, her performance would be better than Elsa. And this problem faced by Elsa is called overfitting problem. She looked at the detailed pattern too much. If she observed a very large number of observations, very close to the population, the observed detailed patterns can be generalized. But with a finite sample, like 100 observations, the detailed pattern could be a local character, not a general trend. Overfitting problem is a problem of a machine like Elsa trying to fit the model to all detailed patterns. Machine learning solution is to find the best in between Anna and Elsa. This is called regularization. Suppose that there is another machine, Christoph. He suggests, hey sisters, why don't we consider the promotion effect when it seems high enough to be sure? I mean, when you observe significant increases with the promotions several times. His strategy can be implemented by imposing a regularizing function that penalizes substantial variance. So most popular supervised learning methods for regression, including ridge regression and lasso, are based on the regularization. So far, I briefly introduced supervised learning with regression. Then, what about unsupervised learning? As I mentioned, marketing has long applied unsupervised learning methods to various research problems. For example, marketers employ cluster analysis for classification and segmentation, factor analysis for customer satisfaction survey analysis, multidimensional scaling to draw a perceptual map for positioning, and nowadays they use topping models to quantify unstructured text data. Then, what about aggregate demand prediction? Of course, marketers use unsupervised learning for research questions related to demand prediction, trend analysis. In exercise 12, you will learn dynamic factor models for trend spotting.